Hello students, in a previous lecture we have started study of practical applications of Bernoulli's equation. Okay, so we shall consider this application to the following measuring devices, which are the Venturimeter, Orificemeter, then Pitot tube, then nozzle meter and rotameter. Okay, in previous lecture we have studied in detail the venturi meter. Now in this lecture we are going to study in detail the remaining devices, that is orifice meter, pitot tube, nozzle meter and rotameter. Okay, so let us start the orifice meter. Okay, so orifice meter is a device which is used for the measuring the rate of flow of the fluid through the pipe. Here is the picture of this orifice meter. This orifice meter is used for measuring the rate of flow of the fluid. Means we are to find the discharge. This orifice meter is used. Okay, this orifice meter consists of a circular plate which has a sharp edged hole. Okay, so this is an orifice plate. Okay, and on this orifice plate a hole is there. Okay, and this hole is called as an orifice. Okay, means this orifice plate consists of the sharp edged hole. Okay, circular sharp edged hole which is called as an orifice, and this orifice is concentric with the pipe. Okay, so this is indicating this orifice. Okay, and the water is flowing through this orifice and comes out to over here. Okay, this is indicating the direction of the flow. This orifice diameter of this orifice is kept generally 0.5 times the diameter of that pipe. Means the diameter of this orifice is half of the diameter of the pipe. Okay, and it is varying from 0.8 to 0.4 to 0.8 times the pipe diameter. Okay, means sometimes it is half or sometimes it is varying from zero point 0.4 to 0.8 times the pipe diameter. This orifice meter is economical and it requires less space for the fitting. Okay, and it is a cheaper device as compared to the venturi meter. Orifice meter is cheaper as compared to the venturi meter. This orifice meter is based on the same principle of the venturi meter. Means orifice meter and venturi meter both are based on the equation Bernoulli's equation, principle of the Bernoulli's equation. Okay, so let us this orifice meter is used to determine the discharge. Okay, so let us see the expression for the rate of flow through the orifice meter. Means the expression for calculating the discharge to this orifice meter. So here is a pipe, in that the orifice plate is placed. Okay, means orifice meter is placed over here. Then the differential manometer is connected at section 1 and section 2. Okay, this section 1 is at 1.5 to 2 times the pipe diameter. Means the distance from the orifice plate up to the section 1 is about 1.5 to 2 times the pipe diameter. Okay, and section 2 is at a distance from the orifice plate of about half of the diameter of the orifice. Okay, means this distance is equal to the half of the diameter of the orifice plate on the downstream side. Okay, so section 1 is on the upstream side of this orifice plate, and section 2 is on the downstream side of this orifice plate. Okay, and the differential manometer is attached at both the sections, at section 1 and at section 2. Due to this due to this orifice plate here, over here the area is contracted, okay, and due to this the velocity is increased, okay, over here, okay. Then the and due to the increased in the velocity, the pressure is also changes over here, okay. The pressure is also changes, and so the P1 is the consider the P1 is an pressure at section 1, and P1 is an section P1, then V1 is velocity at section 1, and the A1 is an area at section 2, okay. And the P2, V2 and A2 are the pressure, velocity and area at the section 2, okay. Then the if we apply the Bernoulli's equation at both the section, then the equation we get P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z1, okay. If we take the velocity terms on the right side and pressure terms on the left side, then we get P1 upon rho g plus Z1 minus P2 upon rho g plus Z2 is equal to V2 square upon 2g minus V1 square upon 2g, okay. This P1 upon rho g plus Z1 minus P2 upon rho g plus Z1 indicating the value of H, means the difference in the pressure head, okay. The value, this is an formula for the pressure head, okay. So instead of writing this, we will directly write the H, okay. Then the equation will become H is equal to V2 square upon 2g minus V1 square upon 2g, okay. This equation can also be written as 2gh is equal to V2 square minus V1 square, okay. Then V2 is equal to under root of 2gh plus V1 square. This is our first equation. Here we have calculated the formula for the V2 velocity at the section 2, okay. But at the section 2 it is an vena contracta, okay. This is a section 2 and this is called as an vena contracta, means section 2 is at the vena contracta. So what is mean by the vena contracta? Vena contracta is the point in the fluid stream where the diameter of the stream is least, okay. Here the flow is flowing through this, and stream is the diameter of this stream is very less over here, okay. And the fluid velocity at this point is maximum, okay. The cross section area is maximum is also minimum, okay. Cross section area is minimum over here, velocity is increased, okay, and the diameter of the stream is very least, then that point is called as an vena contracta, and this section 2 is at the vena contracta. So the A2 represents the area of the vena contracta. Then A0 is an area of the orifice, okay. Here the A0 indicating the area of the orifice. Then the CC means the coefficient of contraction is equal to A2 upon A0, okay. Then this equation can be written as A2 is equal to A0 into CC. This is our second equation, okay. Now if we apply the continuity equation, we have A1 V1 is equal to A2 V2, then V1 becomes A1 upon A2 upon A1 into V2. But we know that A2 is equal to what? A0 into CC, okay. So A0 into CC upon A1 into V2 is equal to V1. This is our equation number 3, okay. So up to here we have calculated the value of V1, V2 and also the A0, sorry, A2 value we have calculated, and we are putting this value into the equation for we have used this value for the equation number 3. Then we get the value of V1 as this. Okay, then the value of V1 we can put in the equation number 1. Okay, the value, substituting the value of V1 in the equation 1, we get V2 is equal to under root of 2GH plus A naught square Cc square into V2 square upon A1 square. If we remove the square root sign, then we get V2 square is equal to 2GH plus A naught upon A1 bracket square into Cc square into V2 square. Okay, means it is equal to V2 is equal to under root of 2GH upon under root of 1 minus A naught upon A1 bracket square into Cc square. Okay, so we calculated the value of V2. Okay, from that we know that the formula for the discharge is A2 into V2. Area into velocity is nothing but the discharge. Okay, so V2 into the value of A2 is A0 into Cc. A2 is equal to A0 into Ct. From the equation 2 we get A2 is equal to A0 into C. Okay, so if we put this over here, then the formula for the discharge is V2 into A0 into Cc. Okay, if we put the value of V2 into this equation then the formula becomes formula for the discharge is V2 A0 Cc under root of 2GH upon under root of 1 minus A0 upon A1 square into Cc. This is our equation number 4. Then this equation is simplified by using CD. CD nothing but the area coefficient of the discharge for the orifice meter. The formula for the CD is equal to Cc in bracket 1 minus A0 upon A1 bracket square upon under root of 1 minus A0 upon A1 bracket square into Cc square. Okay, means Cc is equal to what? CD into under root of 1 minus A0 upon A1 bracket square into Cc square upon under root of 1 minus A0 upon A1 bracket square. Okay, then here we have get the value of Cc. Then put the value of Cc, coefficient of contraction, in the equation number 4. We get the value of discharge as A0 into CD into under root of 1 minus A0 upon A1 bracket square into Cc square upon under root of 1 minus A0 upon A1 bracket square into under root of 2GH upon under root of 1 minus A0 upon A1 bracket square into Cc square. Here denominator and numerator are same, they are cancelled out. The remaining terms will be is equal to CD into A0 into under root of 2GH upon under root of 1 minus A0 upon A1 bracket square. If we simplified this, then we get the final formula for the discharge as CD A0 into A1 under root of 2GH upon under root of A1 square minus A0 square. Okay, this is an equation for the discharge. Okay, here we have calculated the formula for the discharge. Here the CD means what? The coefficient of discharge. Okay, for the orifice meter. Cc means coefficient of contraction. Okay, this coefficient of discharge for the orifice meter is much smaller than that of the Venturi meter. Okay, hope you have understand the expression for finding out the discharge. Okay, so we get the formula for the discharge for the when the flow is flowing through the orifice meter. Okay, so let us solve some numericals on this concept. So first numerical is An orifice meter with the orifice diameter 10 centimeter is inserted in the pipe of 20 centimeter diameter. The pressure gauge is fitted upstream and downstream of the orifice meter gives readings of 19.62 Newton per centimeter square and 9.81 Newton per centimeter square respectively. Coefficient of discharge for the orifice meter is given as 0.6. Find the discharge of water through the pipe. Okay. So we have to calculate here the discharge through the pipe. They have given the diameter of the orifice means D0 is 10 centimeter and diameter of the pipe is means D1 is equal to 20 centimeter. Pressure at both the sections they have given as means P1 is 19.62 Newton per centimeter square and P2 they have given as 9.81 Newton per centimeter square. Okay, with the help of this we have to calculate the discharge. Okay, let us solve the example. Okay, first we will calculate the area for both. The means area of the orifice and area of the pipe. So A naught is equal to pi by 4 into D naught square. Pi by 4 into 10 square, which is equal to 78.54 centimeter square. Then the area of the pipe is equal to pi by 4 into 20 square, which is equal to 314.16 centimeter square. They have given the P1 and P2 values. With the help of this, we can calculate P1 upon rho g, which is equal to 20 meter per of water, and P2 upon rho g, which is we get value of P1 P2 upon rho g is 10 meter of water. Okay, so with the help of this, we can calculate the difference in the pressure head. The formula for this is P1 H is equal to P1 upon rho g minus P2 upon rho g. Okay, so which is equal to 20 minus 10. 10 meter of water is equal to 1000 centimeter of water. Okay, so H means pressure difference is equal to the 1000 centimeter of water, and CD they have given as means coefficient of discharge they have given as 0.6. Okay, then we can calculate now the discharge. Formula for the discharge is Q is equal to CD into A naught upon A naught A1 under root upon under root of A1 square minus A naught square into under root of 2GH. CD is 0.6 into 78.54 into 314.16 upon under root of 314.16 square minus 78.54 square into under root of 2 into G is 9.81. Here is all are in centimeters, so the take the value of G as 981 into H is 1000. Okay, by calculating this we get the value of discharge as 68213.28 centimeter cube per second. Okay, and if we convert this in liter per second, then the value of discharge is 68.21 liter per second. Here is the answer of our question. Okay, then the next problem is an orifice meter with an orifice diameter of 15 centimeter is inserted in a pipe of 30 centimeter diameter. The pressure difference measured by the mercury oil differential manometer on both sides of the orifice meter gives a reading of 50 centimeter of mercury. Find the rate of flow of the oil of specific gravity 0.9 when the coefficient of discharge of the orifice meter is 0.64. Okay, so here they have given the diameters of both of the orifice meter, and also they have given the diameter of the pipe. Okay, Then they have given the readings on the manometer on the both side. The difference in the uh, the reading of the differential manometer, which is equal to 50 centimeter of mercury. So manometer contains the mercury. Okay, and the specific gravity of the oil is 0.9. Okay, then here we have to calculate the discharge. Okay, then the coefficient of discharge are given as 0.64. So with the help of this, we will calculate the discharge. Okay, so first we will calculate the area for both orifice and for the pipe. Okay, so A naught is the area of the orifice, which is equal to pi by 4 into D naught. Pi by 4 into 15 square, which is equal to 176.7 centimeter square. Then diameter of the pipe is they have given as 30 centimeter, and then area of that pipe is pi by 4 into 30 square, which is equal to 706.85 centimeter square. Here they have given the specific gravity of the oil. It means the oil is flowing through the pipe having a specific gravity of 0.9, and the differential manometer is attached to it, which is containing the heavier liquid. It means it contains the mercury. Okay, the specific gravity of the mercury is 13.6. Okay, when the liquid which is in the manometer is heavier than the liquid which is flowing through the pipe, then the formula for the differential head is H is equal to x into Hg upon S naught minus 1 is equal to the value of x is 50 into 13.6 upon 0.9 minus 1 centimeter of oil. The value of H will be 50 into 14.11 means 705.5 centimeter of oil. Okay, the value of H is 705.5 centimeter of oil. CD they have given as 0.64. Okay, now we can easily easily determine the discharge with the help of the formula. Q is equal to CD into A naught upon A naught into A1 under root of A1 square minus A naught square into under root of 2GH. Okay, if we put all the values into this formula, then we get the final value for the discharge is 1374 centimeter cube per second. Now convert it into the liter per second. It is equal to 137.414 liter per second. Next point is the comparison between the orificemeter and the venturimeter. The difference between the orificemeter and the venturimeter. Orificemeter is very simple in construction, whereas venturimeter is relatively complex in the construction. Orificemeter is relatively cheap, whereas the venturimeter is expensive. Then for the orificemeter, the low space is required. Okay, but venturimeter requires the considerable space. Okay, then the pressure recovery is poor in the case of the orificemeter, where the pressure recovery is high in the case of the venturimeter. Coefficient of discharge is varying from 0.60 to 0.65 for the orificemeter. Okay, and for the venturimeter, the coefficient of discharge is varies from 0.95 to 0.99. Okay, for the venturimeter. And the last point is larger power loss for the orificemeter, whereas the for if we consider the loss for the venturimeter, then it is smaller as compared to the orifice meter. Okay, so these are the points for the comparison between the orifice meter and the venturimeter. Okay, so up to here we have studied the second device which is works on the principle of Bernoulli's equation, which is the orifice meter. Now we will see the third device which works on the principle of Bernoulli's equation, which is the Pitot tube. Pitot tube. This device is also used for measuring the this tube is used for measuring the velocity of the flow at any point in the pipe or the channel. Orifice meter and venturimeter are the device used for measuring the discharge to the pipe, whereas the Pitot tube is used for measuring the velocity of the flow at any point in the pipe or in the channel. This Pitot tube is also based on the principle of that if the if the velocity of the flow at any point becomes zero, the pressure is increased due to the conversion of the kinetic energy into the pressure energy. So here is the figure. Okay, and this is an Pitot tube. This Pitot tube consists of an glass tube. Okay, Pitot tube is nothing but the glass tube, and it is bent at an right angle. Okay, means it is an right angle means in the simplest form, if we can say that the Pitot tube consists of a transparent glass tube bent at a right angle, and both ends are unsealed. The ends of this Pitot tube are unsealed. The diameter of this tube is larger enough to neglect the capillary effect. Okay, means the diameter to reduce the diameter of this Pitot tube is designed for design design with the respect to that the pressure the capillary effects are neglected, means keeping in mind that the capillary effects are neglected. Then the one leg of this body is inserted into the flow. Okay, this is an right angle tube, glass tube. One both ends are unsealed. One leg of this Pitot tube is inserted into the flow at the upstream and the aligned with the direction of the flow. Okay, this is aligned with the direction of the flow. And then the whereas the other end here, this is an another end of this Pitot tube, which is called as a stem, and it is vertical and open to the atmosphere. Okay, this is a vertical leg which is called as a stem, and it is open to the atmosphere. The rise in the liquid means liquid is rises in the tube due to the changes in the energy. Here the kinetic energy changes into the pressure energy. Okay, then the let us solve some numericals. Then first we will find out the velocity expression for the velocity. For that, consider 2 points 1 and 2 at the same level in such a way that point 2 is just as an inlet of the point 2 Pitot tube, and point 1 is far away from the tube. Okay, so this is suppose this is an open channel and the Pitot tube is inserted over here. Okay, so now consider 2 points. Point 1 is far away from this Pitot tube, and point 2 is at the opening of this Pitot tube. Okay, means at the inlet of this Pitot tube. Then the P1 is indicating the intensity of the pressure at point 1, P2 is pressure at the point 2. V1 is velocity of flow at point 1, whereas V2 is velocity at point 2. At point 2 the velocity is 0. Here the velocity is 0. Then the H is indicating the depth of the tube in the liquid, and then capital small h indicating the rise of the liquid in the tube above the free surface. Okay, then here when the water is flowing through the pipe, the velocity of the flow at the here the velocity becomes 0, and due to this the pressure is increased due to the conversion of the kinetic energy into the pressure energy. Means at the point 2 the velocity becomes 0. Okay, and here the pressure energy is converted into means kinetic energy is converted into the pressure energy. Okay, because of this the pressure is increased at the point 2. Okay, then small h and capital H indicating the depth of the tube in the liquid, and capital H small h indicating the rise of the liquid in the tube above the free surface. Okay, if we apply the Bernoulli's equation at both the sections, okay, then the equation is P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. Here the pipe is horizontal, both points are on horizontal, so Z1 is equal to Z2. Both the points are lying on the same line. Okay, so these are equal. Z1 is equal to Z2, and the V2 is here 0 because of the changing the kinetic energy into the pressure energy. Here the velocity at point 2 is 0, pressure is increased at the point 2. Okay, so value of P2 is 0. Then P1 upon rho g means pressure head at point 1 is equal to capital H, and P2 upon rho g is equal to H means small h plus capital H. Okay, means pressure head at the point 2 is capital H plus small h. Okay, if we put this value into the Bernoulli's equation, then we get H plus V1 square upon 2g is equal to H small h plus capital H. Okay, V2 is 0, so this term will be 0. Z2 is Z1 and Z2 are equal, so they are cancelled out from both sides. The remaining terms are P1 upon rho g, instead of we are writing as H, means H plus V1 square upon 2g plus instead of P2 upon rho g we are writing as H small h plus capital H. So we get H plus V1 square upon 2g is equal to small h plus capital H. Then the small h is equal to V1 square upon 2g. Okay, means V1 is equal to under root of 2gh. Okay, then this is we get the formula for the V1, but this is an theoretical velocity. Okay, this is an theoretical velocity. Then the actual velocity is given by the equation V1 is equal to means V1 actual is equal to CV into under root of 2gh. This CV is nothing but the coefficient of this Pitot tube. Okay, then the velocity at any point is equal to means V is equal to CV into under root of 2gh. This is the formula for calculating the velocity at any point. Okay, with the help of the Pitot tube. Then the next point is the velocity of flow in the pipe by the Pitot tube. For finding the velocity at any point in the Pitot tube, the following arrangements are adopted. Okay, so these are the figure indicating the arrangement of the different arrangements of the Pitot tube. So first figure indicating that the Pitot tube is showing the Pitot tube along the vertical piezometer. This is an Pitot tube and is with the piezometric tube. Okay. Then second figure means indicating the Pitot tube connected with the piezometric tube. This is an Pitot tube, okay, and it is connected with the piezometer tube. Then third, the Pitot tube and the vertical piezometer are connected with the U2 manometer. Okay, this is an Pitot tube, and here is an piezometer, and it is connected with the U2 manometer. Okay, and last arrangement is the Pitot static tube. Okay, this is indicating the Pitot static tube, which consists of the two circular concentric tubes. Okay, these are the two tubes, two circular concentric tubes, one inside the other with the some annular space between. The outlet of these two tubes are connected to the differential manometer, where the difference in the pressure head is H. Okay, this is a difference in the pressure head is the H is measured by knowing the difference of levels of manometer liquid, say X. Okay, readings is we are taking with the as an X. Reading of the differential manometer is indicated by X. With the help of this reading, we can calculate the difference in the pressure head. Formula for this is H is equal to X in bracket Hg upon S0 minus 1. Okay. Now we will solve the numericals on the Pitot tube. So first problem is a Pitot static tube placed in the center of the 300 mm pipeline has one orifice pointing upstream and another perpendicular to it. The mean velocity in the pipe is 0.80 of the central velocity. Okay, find the discharge to the pipe if the pressure difference between the two orifices is 60 mm of water. Take the coefficient of Pitot tube as Cv is equal to 0.98. So here the arrangement of the Pitot tube is means here the Pitot static tube is there. Okay, means two concentric tubes are there. Okay, the arrangement will be look like this. Okay, then they have given the diameter of the pipe as 300 mm and difference in the pressure head as 60 mm of water, means 0.6 meter of water. Cv means coefficient of Pitot tube they have given as 0.98. Okay, they have given the mean velocity is 0.80 of the central velocity, means they have given the relation between the mean velocity and central velocity as mean velocity is equal to 0.8 of central velocity, but we don't know the value of central velocity. So first we will calculate the value of central velocity. So Cv central velocity is equal to formula Cv into under root of 2gh is equal to 0.98 into under root of 2 into 9.81 into 0.6. We get the value of central velocity as 1.063 meter per second. Okay, and then here we get the value of central velocity. Now we can identify the value for the mean velocity. Okay, so mean velocity is equal to 0.80 into the central velocity, which is equal to 1.363. Okay, so the central velocity is equal to 0.8504 meter per second. Okay, then the discharge is equal to what? Area into velocity. We have to find out the discharge. Then the formula for the discharge is Q is equal to AV. area into velocity. Mean velocity we have calculated. We have to first calculate the area. Area is nothing but the pi by 4 d square, means pi by 4 into diameter of the pipe is 30, 0.30 meter. Okay, means pi by 4 into 0.30 square into mean velocity is 0.8504. We get the final value of the discharge as 0.06 meter cube per second. Next problem is find the velocity of the flow of an oil through a pipe when the difference of mercury level in the differential U-tube manometer connected to the two tappings of the Pitot tube is 100 mm. Take coefficient of Pitot tube 0.98 and specific gravity of the oil as 0.8. Okay, so what we have to calculate here is the velocity of the flow. Okay, they have given the value of readings of the differential manometer level is 100 mm. Okay, means x value of x is 100 mm, which is equal to 0.1 meter. Coefficient of Pitot tube they have given as 0.98. So U-tube manometer is connected. Okay, then the specific gravity of the and this manometer contains the mercury. Then specific gravity of the mercury is 13.6. Specific gravity of the oil they have given as 0.8. Okay, so with the help of this we can calculate the difference in the pressure head. Formula is F is equal to x into Sg upon S naught minus 1 bracket complete is equal to value of x is 0.1 into 13.6 upon 0.8 minus 1. So we get the difference in the pressure head has 1.6 meter of oil. Then we can calculate the velocity of the flow. Formula is Cv under root of 2gh. Cv means the coefficient of the Pitot tube, which is 0.98 under root of 2 into g is 9.81, means acceleration due to gravity. H value we have calculated, which is 1.6. So we get the value of velocity as 5.49 meter per second. Next problem is a Pitot tube is used to measure the velocity of the water in a pipe. The stagnation pressure head is 6 meter and static pressure head is 5 meter. Calculate the velocity of the flow assuming the coefficient of tube is equal to 0.98. So here they have given the arrangement of the Pitot tube as means Pitot static tube is there. Okay, means two concentric tubes are there, and the stagnation pressure head is means HS is 6 meter and stagnation pressure static pressure head means HT is 5 meter. Okay, then we have to calculate the velocity of the flow, and they have given the coefficient of the tube is 0.98. So first we will calculate the pressure difference in the pressure head. Stagnation pressure is 6 meter, static pressure is 5 meter. So difference in pressure head is 6 minus 5 is equal to 1 meter. Okay, then velocity of the flow formula is V is equal to Cv into under root of 2gh. Cv they have given as 0.98 under root of 2 into g is 9.81 into h is 1. So we get the velocity of the flow as 4.34 meter per second. Okay, now we will solve one more last problem on the Pitot tube. The formula is a submarine moves horizontally in the sea and has its axis 50 meter below the surface of the water. A Pitot tube properly placed just in front of the submarine and along its axis is connected to the two limbs of the U-tube containing mercury. A difference of mercury level is found to be 170 mm. Find the speed of the submarine knowing that specific gravity of the mercury is 13.6 and that of the seawater is 1.026 with respect to the fresh water. So here we have to calculate the speed. Speed is nothing but the velocity. So here we have to calculate the velocity. They have given the difference in the mercury level as means 170 mm, okay, which is equal to 0.70 meter. Then the U2 manometer containing the mercury. So the specific gravity of the mercury is 13.6 and the specific gravity of the seawater they have given as 1.026. Okay, so with the help of this we can calculate the difference in the pressure head. So H is equal to X into Sg upon S naught minus 1. Value of X is 0.17 into in bracket 13.6 upon 1.026 minus 1. We get the value of H as 2.0834 meter. Formula for the V is under root of 2gh. Okay, so it is equal to under root of 2 into g is 9.1 into h is 2.0834 6. Okay, then we get the value as 6.393 meter per second. Convert into the kilometer per hour, which is equal to 23.01 kilometer per hour. Hope you understand all these problems well. Okay, next instrument is means fourth instrument or the fourth device which is works on the principle of Bernoulli's equation is rotameter. This rotameter is also called as a variable area meter, and this rotameter is used for measuring the discharge of the flow through the pipes. Okay, means Venturimeter, Orificemeter and also the rotameter is used for measuring the discharge through the pipe. This rotameter consists of an vertical tempered transparent glass. Means all this rotameter is made up of the glass. Okay, and means graduated glass, and it contains an interior float which has a sharp circular upper edge. So this is an float and its upper edges are circular and sharp. This float is heavier than the liquid. Okay, this float is heavier than the liquid which is flowing through this rotameter. Okay, and due to this it is sink to the bottom of the tube when the fluid is in the rest. Okay, when water is inserted from here and it is means here it is an inlet and over here is an outlet. Okay, and when the water is inserted in the rotameter, due to its heavy weight than the liquid which is flowing through the rotameter, it is this float is sink to the bottom of the tube when this fluid is at the rest. The grooves cuts into the circumference of the float, cause it to rotate and thus it remains central in the tube. Okay, the float displaced up due to the upward flow through the tube. This tube is graduated to read the rate of the flow directly. Okay, so with the help of the rotameter we can directly find the value of the discharge, means the rate of the flow. Okay, so next device which is based on the principle of the Bernoulli's equation is the nozzle meter, or we can say the flow nozzle. Okay, this is also used for measuring the discharge. This is somewhat similar to the Venturimeter. Okay, this in the figure you can see this is an flow nozzle. It is consist of an streamline conversion nozzle. Okay, this is an streamline conversion nozzle. The fluid gets accelerated to the minimum friction and obstruction to the flow. Okay, here the means it is look like as an venturimeter. Only the difference is here in between these two is the diversion part is omitted over here. Okay, and the conversion part is here, but here the diversion part is omitted. Okay, so basic equations are similar to the venturimeter. Because of the diversion part is omitted in this nozzle meter, the dissipation of the energy on the downstream side of the throat is greater than the venturimeter, and here the coefficient of discharge is not depends upon the changes beyond the throat, so that it is almost same as that of the venturimeter. Okay, so this flow nozzle is essentially a venturimeter. Only difference is here the diversion part is emitted. Okay, so both are based on the uh, both are used for the measuring the discharge, means the rate of the flow. Okay, only the dissipation of energy is more in the case of the flow nozzle. Okay, so due to this flow nozzle is superior than the venturimeter, as the diversion part is neglected here. Okay, so it is flow nozzle is cheaper than the venturimeter. Okay, now we will stop over here. So in this lecture we have seen the remaining four devices which works on the principle of Bernoulli's equation: orifice meter, then we have seen the Pitot tube, then rotameter, and last one we have seen as a flow nozzle or the nozzle meter. Hope you understand all these points in well. Okay, thank you.